Good morning, everyone. I'm Kang. Today, I'm going to talk about the phenylbutyrate rescue of SLC1 mutation in patient-derived cell and mouse models. I'm so inspired by Whitney's story. I'm so happy. So I would like to start with a story. In 2011, I got a Victor Award for phenylbutyrate as a novel treatment for epilepsy. I presented data at Vanderbilt. At the end, Dr. Tom Davis, a professor of neurology, questioned me, why don't you direct using patient? What are you waiting for? But I could not, because there's a big gap between some finding at the bench level to clinical application. So 2018, I met Dr. Jinel in a yoga class, and he was VP of Stoke Therapeutics. I know Stoke has a Tango technology to restore wild-type allele for Dravet syndrome, the sodium channel mutation. So I sent him a list of genes, including GABA-A receptor and GABA transporter, including SLC1A. And then he emailed me back. He said, do you study SLC1A? I said, yes. I said, do you know Amber Freed? She has a son with a mutation. I said, I do not. So we got connected. After I learned Amber's story, I feel she may benefit from talking with my friend, Terry Jiu. She has a son with Angelman syndrome. She has already gone through all these struggles and challenges. So I connected Amber and Terry Jiu. Later on, we talk a lot with Amber. I know the struggles. So I asked Amber, if there's no good drug, maybe you could try PBA. I see good efficacy in Maxwell cells. So and then we talked with Terry Jiu, and Terry Jiu connected us with Dr. Greenspan. So, and then later on, Scott and then Kim, so this is how the story got started. So we all know the story about Lita Maxwell. So I like this picture. I got a mutation, let's fight. So this is why I joined the fight with Maxwell. So we know right now that about at least 80 established epilepsy genes, about 1,000 epilepsy-associated genes. So Maxwell is just one of the kids. SLC1A is just one of those mutations. So before SLC1A, we studied GABA-A receptor. There are many genes, mutation in GABA-A receptor. The family has 18 subunits, about 10 of them associated with epilepsy. So what does it mean if a child diagnosed with mutation in SLC1A? It may lose function, gain function, or change the function. So how do we study the impact of mutation? There are many ways for us, because we studied GABA-A receptor for over 2 decades. So we built a lot of tools and protocols. So we borrowed that for SLC1 mutation. So in lab, we use HEC cells, neurons, astrocytes. Most recently, we use iPSC, patient-derived cells. So this is just to give you some example about GABA-A receptor mutation we have studied. We have studied at least about 100 of them. The work is largely in collaboration with my mentor, Dr. McDonough. He is the king of GABA-A receptor. So for GABA transporter, we studied about 60 mutations. So, this just to give you some example. In the past few years, we have published 6 papers. We report a portion of our work. This paper in Brain was published last year. We showed 22 mutations. These 22 mutations associated with a very wide range of phenotypes: autism, epilepsy, neurodevelopmental delay, you name it. Surprisingly, compared with the wild type, all these mutations, regardless of phenotype, they all have either loss of function or severely reduced function. So that's very interesting. And then we wonder what can cause the mutant transporter to lose function. So we got good help from 2. So Professor Xu and Dr. Wang. Professor Xu is a pioneer for protein folding and misfolding using machine learning. He's exporting AlphaFold. And Dr. Wang is a former trainee of Professor Xu. We have been collaborating with GABA-A receptor for almost 10 years. So we move on to GABA transporter. We modeled every single mutation. Amber passed on to me. This is just to show some example from a Chinese cohort, the kids associated with myoclonic atonic epilepsy. So with 7 different AI tools, we predict the mutant protein have a reduced protein stability. We published this work. And this is Charlie's mutation, A2A. So if you have a mutation from adenine to valine, you will see they add a side chain, so make the protein much more hydrophobic and aggregation prone, and also lose the stability. So the common features identified in mutant protein by machine learning is increased hydrophobicity, decreased protein stability, based on all this the modeling. So how can we rescue this mutant transporter? So where is the mutant transporter? So we have screened 11 small molecules, include PBA. So this is why I identified the PBA. So we know GABA transporter is a transmembrane protein. If you want to have function, it must be at the cell surface. So it must reach cell surface, otherwise it's not useful. And then you look at the mutant transporter. So this is Maxwell's mutation, compared with the wild type in left astrocytes and the neurons. So the reason we use both astrocytes and neurons is because in the brain, the GABA transporter is expressed in both astrocytes and the neurons. So these were live cells. So compared with the wild type, the mutant one is clearly stuck around the nuclear envelope. So I have an arrow to show. They must reach the edge so they can have function. So if they are stuck inside, then they won't perform any function. So in the same in astrocytes and neuron. So when we study gene mutation, we often ask where the mutant allele interfere with the wild type allele, is any dominant negative suppression on the mutant and wild type allele. So we look at the wild type and we look at mutant. So we co-express the wild type and mutant. So here you can see, compared with the wild type, this is a different mutant. So one is Maxwell's. You see, in astrocytes, the mutant one form large clump. So that's clearly different compared with the wild type. And then we know all this mutation is germline mutation. So baby have that mutation since conception on. So basically, you have that mutation at the very beginning of your life. So at what time, but this mutant protein got produced because we know the mutant protein is not a function normally. So we look at the iPSC cells. This is way before we differentiate them into astrocytes or neurons. So you can see the cells are very compact. So at that level, when the cells with high pluripotency, like as stained with OCT4, we see very clear, even although it's low level of GAT1. So we use the biochemical approach is validate. So the protein actually is present at the very beginning of your life, at the stem cell stage. So this is why we test the PBA effect in various cell types. So this reflects a different stage of differentiation. We include iPSCs, neuroprogenitor cells, and GABAergic neuron, and astrocytes. So these are the cells before experiment is all live cells on the day of experiment. So this is Maxwell's neuron and astrocytes. So look pretty nice. And then we stained with the synaptophysin, which is a marker to mark synapse. So we can see, compare with corrected is his own cells, but with CRISPR corrected, so use as a genetic control. The Maxwell cells have clearly reduced puncta, suggesting the mutant, the protein have reduced presence at the synapse. Similarly, in astrocytes, again, we look at both neuron and astrocytes. In his astrocytes, you see reduced GAT1 expression. If we view in live cells, compared with the wild type, you see pretty smooth distribution around the edge, but the mutant is more stuck inside, like around the nuclear region. And this is just one mutation. How about the other mutations? So we use the high throughput method, like a flow cytometry, to look at the multiple mutations. We wonder if the mutant protein can reach cell membrane at the cell surface. And compare with wild type. The mutant cross mutations, we show 10 here. They will have a reduced surface expression. However, at a total level, the expression is more variable. Some maybe have a similar level as the wild type. And then we look at the function restoration. So we look at the GABA uptake. So here you can see we test 8 mutations here. First we look at the homozygous condition, means the mutant condition alone. And then we look at the mixed, we call the heterozygous. So in all the cases, it's heterozygous. So this is a patient condition. So we look at all these mutations. We see the upregulation of GABA uptake in wild type and in all the mutations throughout. And then we wonder, in heterozygous patient, which allele is rescued? It could be wild type or could be the mutant. So we differentially tag the wild type and the mutant. So the wild type is tagged with HA, the mutant is tagged with YFP. So the lower panel, you will see the wild type. It's a very clear one band. But for the upper level, you see the mutant is very variable. The reason is because we include both missense mutation and nonsense. Those nonsense generate premature stop codon at the N-terminal or C-terminal. So this is why you see various protein expression. And then we quantified each allele, how much compared with the vehicle treated. The vehicle we mean stem cell. So all the look at the HA. In all the conditions, HA is upregulated in both wild type and the mutant. And however, look at the GFP, which is in mutant condition. The mutant allele, some is upregulated, some is downregulated. So this way, maybe in patient, some patients may have a different, better response than others. But the good news is every single one we see upregulation because you have a wild type allele. Because so far, I think as far as I know, all the kids with SS mutation is heterozygous. So you will have a wild type copy. So that one can be upregulated. So you will have hope from there. And then we in lab ongoing work we're testing about 30 mutations. We want to see if we see common pattern. And then we move on to mouse models because we want to see in vivo if we see efficacy. So we look at Charlie's mutation and then Maxwell's mutation. So Charlie's mutation is A28V. That one has, we know, have about 30% remaining function. USA poster, we show more details about these mutations. And Maxwell's mutation is complete loss of function, has no function at all. And then in collaboration with Roche, we did a tigabin binding. So tigabin is a GAT1 specific inhibitor. So we want to see what's the GAT1 expression level. So this is the sagittal section. You can see pretty robust signal throughout the brain. The yellow stands for strong signal. So here you see GAT1 expression from cortex, hippocampal, thalamus, to cerebellum. The lowest expression is stratum. And then look at the Charlie's mutation. So compare with the wild type, Charlie's mutation has reduction across all different brain regions. So look at the quantification. Cortex, hippocampus, thalamus, cerebellum, you see all about 50% reduction. So I saw some colleagues from Allen Brain Institute. That would be very useful as your map with the GAT1 expression. And then look at the Maxwell's mutation. Very similar data as the Charlie's. Compared with the wild type, you have global reduction of the GAT1 expression. It's all less than 50%. And then we did a EEG recording. We know in kids, the Kim good speed, also others, they will have absence seizures. And in mouse, in rodents, 5 to 7 hertz is the most correlate of human absence. So we use 5 to 7 hertz. We identified both mouse model have absence epilepsy. So this is Charlie's mouse. This is Maxwell's mouse. And then we look at the GAT1 expression, use biochemistry to see if the expression level is changed. So we get a consistent data as we see from like a tigabin binding. So we see global reduction in both mouse models. The change is about 50%. So it's very similar. And so how can PBA, if PBA can rescue GAT1 expression? So we treat an animal either for vehicle or for PBA with 100 milligram per kg for 7 days. And then compare with vehicle-treated and PBA-treated in both Charlie's mouse and Maxwell's mouse, using modest but very consistent upregulation in cortex, thalamus, and the hippocampus. So we did not see a big change in cerebellum. I think cerebellum, because the expression level is relatively low, so yeah, we do not exclude as any maybe experimental artifact. So anyway, cortex, thalamus, hippocampus, this is pretty clear. And this for EEG recording, we wonder if PBA alone can mitigate the seizures. We know like acetoxamide, valproic acid, a lot of drugs, but we tried the PBA and we also compared with other drugs. Here we just report PBA alone, 100 milligram. We use the same protocol we used for biochemistry. This earlier work already published. In 6 mice, all the mice have a clear reduction. The average reduction level is 76% in mouse model. So as you can see, we have a pretty large program in our lab on SLC1A mutations. Our ongoing work right now, we are doing longitudinal monitoring of the effect of a PBA on neurobehavior phenotype in both mouse models. We also do longitudinal monitoring of the effect of PBA on glutamine and GABA level. So it'll be very interesting to chat with Kim about the finding in human kids. We also are doing like some electrophysiology work. Our postdoc, Curry, he's going to present his work later today. In addition to that, we are testing a dual therapy because we know one drug is not enough. And we also don't know in the long-term how the drug works. So we're testing a dual therapy, and Carson has a poster for that. Our goal is just like everyone in the room. We want to find a cure with help with everyone. And so the take-home message is we identified partial or complete loss of function is common across SLC1 mutations, regardless of clinical phenotype. We also found mutant GAT1 is retained inside the endoplasmic reticulum in both neurons and astrocytes across mutations. And we found that PBA alone can restore GABA uptake in cell models and also can mitigate the seizures in both mouse models. We found the PBA can probably beneficial for most of patients, if not all. So that's very good news because PBA can operate the wild type allele. And we found the effect of PBA on the mutant allele is mutation dependent. And I'm very thankful to everyone in my lab. They really work hard, including previous trainee, and Felicia and Marsha. Actually, I'm so glad he came back from Nebraska to join this symposium. We're very grateful for the Patient Foundation, SLC1A Connect. I really like the word connect. It connect us as a very nice community, and Amber did such wonderful job. We're very inspired by many patients and parents. The story really help us understand the disease and help us doing good research. I'm very thankful to many industry partners. UCB, I know some colleagues are here. And Roche, BioMarine, Taysha Gene Therapy. Some found my lab, some just simply have a good discussion with me, so we learn from you. And we are benefiting from talking with many physicians, many in America, like Dr. Greenspan, Dr. Goodspeed, Scott, Rob, and Emma from Vanderbilt. Also, now we have published a paper together. Also, I'm benefiting from many physicians from China. Lastly, I want to share you like 4 Chinese character that's called 不忘初心, means do not forget the original intention. So I'm trained as a physician scientist from China. So the guy, Professor Ryan, is my mentor. He's a very renowned epileptologist. So he has one time have 3 girls, we call the academic sisters. At a dinner party, he talked with us. He said he has no lab because back then in China, it's very little research ongoing. So a lot of patients has no good response to drugs. So the drug is not very good. So you all must work hard to find a better treatment. and in 20 years. So Xiaohua, the one in the middle, now become president of medical school in Wuhan University. The one at the right side, Xiaosan, she's my roommate. She's the president of Brain Hospital in Nanjing Medical School. I took a different route, came to US. I hope I have worked hard and find a better drug. Time will tell. Yeah. Thank you.